Greetings, fellow humans. Today I'd like to tell you about positioning systems for indoor robots. Indoor robots are becoming increasingly popular and have a wide range of applications, from home cleaning robots to industrial automation. However, navigating indoors presents unique challenges compared to outdoor navigation, such as limited line of sight and more confined spaces. That's why positioning systems are critical for indoor robot navigation. There are three main types of positioning systems for indoor robots. You've got your initial measurement units, also known as IMUs. You've got your simultaneous location and mapping, or SLAM. And then there's wireless systems such as Wi-Fi or Bluetooth. IMUs are composed of sensors that measure the robot's acceleration, rotation, and magnetic field to determine its position and orientation. SLAM, on the other hand, involves mapping the robot's surroundings using sensors and then using that map to navigate. Lastly, wireless systems use signals from Wi-Fi or Bluetooth to triangulate the robot's position. So let's take a look at each of these positioning systems in a little more detail and see what makes them tick. Inertial measurement units, or IMUs for short, are commonly used for indoor robot positioning. An IMU is a small electronic device that contains a combination of sensors such as accelerometers, gyroscopes, and magnetometers. These sensors work together to measure the robot's movement, orientation, and magnetic field. IMUs work by measuring changes in velocity and direction to calculate the robot's position and orientation. For example, the accelerometer measures changes in the robot's velocity, while the gyroscope measures changes in its orientation. By combining these measurements, the IMU can estimate the robot's current position and orientation. One advantage of using an IMU for indoor robot positioning is that it is a self-contained system, meaning it does not rely on external infrastructure. This makes IMUs ideal for applications where a robot needs to navigate in areas where GPS signals are weak or unavailable. However, IMUs do have some limitations. One limitation is that the accuracy of the position estimate decreases over time due to error accumulation. This is known as drift, and it can cause the robot's position estimate to become increasingly inaccurate the longer it operates. Another limitation is that IMUs are sensitive to vibrations, which can cause inaccurate measurements. I like to call IMUs the hostage positioning system because it's basically what you do when you find yourself bound, gagged, and blindfolded in the trunk of a moving car. Again, basically, if you know your starting point and pay attention to acceleration, deceleration, and turns, you can still have a pretty good idea of where you are. Simultaneous localization and mapping, or SLAM for short, is another popular positioning system for indoor robots. SLAM works by using sensors such as cameras, LiDAR, and sonar to create a map of the robot's environment in real time. The robot can then use this map to localize itself within the environment and navigate to its destination. SLAM algorithms use the robot's sensor data to create a map of the environment as the robot moves. As the map is being created, the robot also estimates its position within the environment. This process is iterative, with the robot continuously updating the map and its position estimate as it moves. One advantage of using SLAM for indoor positioning is that it can work in unknown or dynamic environments. Because SLAM is creating a map of the environment as it moves, it does not require a pre-existing map of the environment. This makes SLAM ideal for applications where the environment is changing, such as in a warehouse where boxes are constantly being moved around. However, SLAM does have some limitations. One limitation is that SLAM requires a lot of computational power, which can make it difficult to implement on low-power devices. Another limitation is that the accuracy of the map and the robot's position estimate can decrease in areas with poor sensor visibility, such as in low-light environments. SLAM works very well in conjunction with IMUs. In fact, using a combination of approaches increases overall accuracy by allowing the subsystems to correct or constrain each other. Let's take a look at a third positioning technique, using wireless systems. Wireless systems, such as Wi-Fi and Bluetooth, can also be used for indoor robot positioning. These systems work by using signals from access points or beacons to determine the robot's position. Wi-Fi positioning systems work by using the signal strength and timing of Wi-Fi access points to estimate the robot's position. This technique is known as Wi-Fi triangulation. Bluetooth beacons, on the other hand, emit a signal that can be detected by the robot's sensors, and the distance to the beacon can be estimated based on the strength of the signal. One advantage of using wireless systems for indoor robot positioning is that they are relatively inexpensive and easy to implement. Wi-Fi and Bluetooth access points are common in indoor environments, and the hardware required to detect these signals is readily available. However, wireless systems also have some limitations. One limitation is that they can be affected by interference from other wireless devices in the environment. This can cause inaccuracies in the robot's position estimate. Another limitation is that the accuracy of the position estimate can be reduced in environments with a high density of obstacles, such as walls or furniture. Despite these limitations, wireless systems are still a popular choice for indoor robot positioning, especially in applications such as retail and hospitality, where the robot needs to navigate in environments that are relatively static and have a moderate density of obstacles. As we have seen, there are several different types of positioning systems for indoor robots, each with its own unique advantages and limitations. However, the future of indoor robot positioning lies not only in these individual systems, but also in the integration of these systems with artificial intelligence. By combining the data from multiple positioning systems with AI algorithms, indoor robots can achieve even greater accuracy and robustness in their navigation and localization. AI can help to reduce errors and uncertainty in the positioning data and enable the robot to adapt to changing environments in real time. In addition, AI can help to optimize the robot's path planning and navigation, taking into account factors such as obstacles, traffic, and efficiency. This can lead to more efficient and more effective use of indoor robots in various applications, from healthcare to retail to warehouse automation and manufacturing. So, as the field of robotics continues to advance, we can expect to see even more sophisticated positioning systems powered by AI that will enable indoor robots to navigate and operate in a wide range of indoor environments with greater precision and autonomy.